So why get it into this summation notation? It's such a fuss. It's so difficult. And the reason why is it allows us to, instead of having these giant rectangles, which are pretty not very good approximations, I mean, they're kind of close. But imagine, if we're going to do it by hand, it would be a lot of work if we made a bunch of little rectangles. And let me show you, why would we want a bunch of little rectangles? Well, if we look at this video real quick. So we're going to try to estimate the area under the curve using Riemann sums. And you can see as we get more rectangles, as they get smaller and smaller and smaller, they fit the curve a lot better and give us a much better approximation. And not only that, if n goes to infinity, you're going to actually get the perfect area under the curve. So let's take a look at the formula that we have here. So this is called an integral. In other words, the antiderivative. We've talked about how that's the area underneath the curve. So we can evaluate this antiderivative using a Riemann sum, and I'd hate to tell you guys, a limit is that as n goes to infinity. So remember that Riemann sum, this is base times height. It really doesn't matter if we do a right or left-hand sum because we're going to make it perfect. We're going to use an infinite amount of little tiny rectangles. And that's what's cool about delta x. Notice b minus a over n is self-adjusting. As n goes to infinity, that's going to make delta x super small. It's going to take our width of the rectangle from some large value, and it's just going to keep making it smaller. And as n goes to infinity, we basically have no width to our rectangles, and we're filling it with these rectangles with almost, really with no area. So it's kind of interesting how that works. But this is very similar formula to what we used in the previous video. So it's just the base times the height. They just flip this around a little bit. Same exact formula in that sense. We're just going to put a limit in front of it, and we're not going to be so focused on if it's a left or right hand sum. We're just going to the right hand sum and going right with this formula. And if you can evaluate this sigma, there are special ways to evaluate this, and I don't think we're doing that this year, but later on in your math journey you're going to learn there's ways to evaluate these limits and these sums. And honestly, there's only special cases if that happens, and we're more likely to resort to just using computer programming and getting something close. But anyways, let's look at that formula and fit it in here. So which of the following is equivalent to the following definite integral? So b and a, realize something right here. B and a are given right here on the bounds. That is a and that is b. So let's start with our delta x. So we already kind of know that formula from the last assignment. So the limit, let me write it all. So we have the integral, or antiderivative. We're going to call it an integral though, of f of x dx. And that's what's cool. This is actually showing us where that notation's from. When we get to this notation later on, there's always going to be this dx at the end. Remember how whenever we'd find the derivative, we put d dx? That dx is always there to represent, what we're taking the derivative in respect of. But here, it's showing you that represents delta x, the width of each rectangle. So it actually has a place in this formula. And then we're going to say that that's the limit as n goes to infinity of, and then sigma, we're going to have I equals 1 to n f of xi times delta x. So let's start with our delta x. So delta x we know is b minus a over n. So in this case n, we're just going to keep it as n. And b minus a, for ours it's going to be 0 to pi, so it's going to be pi minus 0. I don't know why I put a. Over n, so pi over n. That's our delta x. So remember, this is a on the bottom, this is b. Make sure you really get that down. Okay, now let's figure out what xi is. So xi is a, same thing, a plus delta xi. I don't know why I needed to look at it. Delta x times I, actually. So a was 0 plus delta x pi over n times I. So that's pi over n I. So we're just going to substitute that into the formula. So this limit here, or not this limit, it's going to equal, so that integral is going to equal the limit, if I could write, as n goes to infinity. then our sigma I equals 1 to n. And then f of x is sine of x, so we're going to do sine of xi, which is pi over n I. And then times delta x is pi over n. So let's find that one. Pi I over n, pi over n. This one's looking good right here. And there you go. This one, same exact idea. You just, a is 0, b is 3. Shouldn't be too difficult. Alright, let's look at this one. This one's going backwards. Not really so much fun, to be honest, but notice b minus a. This is our delta x. Kind of go a little backwards here. Delta x equals b minus a over n. Alright, so b minus a, if we subtract b and a, it's going to be 5. So which one of those have a 5? 5 minus 2 is 3, 7 minus 0 is 7, 5 minus 0 is 5, and 7 minus 2 is also 5. So we're kind of, we know these are out. So we're kind of looking at these two here. Now, we also know, though, that xi, in this case, if natural log of x was our function, then xi is a plus delta xi, right? So that would be a plus 5 over ni, because we know delta x is 5 over n, right? So if I were to take a plus 5 over ni, which is what we have here from our formula, and set it equal to the inside here, you'll see that a is 2. You subtract this to the other side, it cancels out, and you would get a equals 2. So that tells us our lower bound must be 2, our upper bound must be 7. Same idea here. You could probably guess that 4 is our a, right? So it's probably going to start at 4. And 5, once again, 5 is the distance. So it looks like b, although it could be d, but you go back and double check those. If xi is a plus delta x, then that's what's going to give that summation in there. So you don't need to be doing 4 plus that. Because if you had this as a, that would give you 4 plus, and then if xi was 4 plus delta xi, then the inside would end up being 8. So that's why this one wouldn't work. It's adding an extra 4. You're taking this here and substituting it in for x, and that's what's going to give you this here. So once again, kind of think about that. Those are a little bit more difficult. I think these are a little more straightforward. Just plug it right in.